Welcome to Exoplanet Transits. Our group was led by or mentored by Dr. Thomas P. Rutherford, and our group is composed of
Sohum Gautam.
Samanya, Girish.
Ethan Liu.
Myneni.
Andrew Rebello,
Hridaya, Saravanan.
Luke Thomann.
First, let's dive into what exoplanets are. They're planets that orbit stars other than our sun. Now, there are many methods, but we're going to talk about the five most important. The first is radial velocity. Now, this is using the Doppler shift to derive information about its period and velocity. Next, we have the transit method. Now, this is the method we'll be using, and we watch for dips in the absolute magnitude light curve. Next, we have the direct imaging, which is essentially taking pictures. We then have gravitational lensing, where we use we use the ability of light to curve around large masses as a gravity lens in order to detect exoplanets far away. And finally, astrometry, which is basically watching for wobbles in the host star of that exoplanet. Let's move on to the exoplanet history. In January 1992, the first exoplanets were discovered by Wollaston and Frail. In 1999, we observed the first transit independently led by Charbonneau and Henry. And lastly, in April 2001, the first exoplanet was discovered in the habitable zone. Now, this is the zone where it's not too hot or too cold for life, and conditions are, at least for life as we know it as humans, and it was in that zone that was just right to facilitate life. Next slide.
These are some of the primary reasons why astronomers conduct research on exoplanets. By researching exoplanets, we can find Earth-like planets in other star systems, and if they are in the Goldilocks zone, as in within the appropriate range of distance from a target star, they could potentially support life. Also, studying exoplanets can give us insights into the planetary processes that occurred in our own solar system during its formation, including that of the Earth. Finally, as the search for exoplanets continues and we find new ones that are potentially habitable, we also continue to attempt to answer the question of, are we truly alone in the universe? Next slide. The most common way of detecting exoplanets is through the transit method. To detect a transit, the observing instrument, such as a satellite or in our case, a ground telescope, must be recording the magnitude or brightness of its target star over an interval of time. In the animation shown, we can see how graphing the brightness versus time data can produce a light curve, which can tell us more about the transiting exoplanet and its host star. Next slide. When graphing the magnitude of the star over a given time interval, if an exoplanet is transiting the star during that time, a dip should be visible in the light curve graphed. The depth of the graph transit depends on the size of the exoplanet and the size and brightness of the star. In the two cases shown on this slide, we can see exoplanets of the same size transiting a brighter star on the left and a dimmer star on the right. The transit on the left will produce a shallower light curve because since the star is relatively brighter and more massive, the exoplanet will block a lesser percentage of the star's light as it transits. On the other hand, the transit on the right will produce a much deeper light curve because even though the exoplanet is the same size as the one on the left, it will block a larger percentage of the dimmer, smaller star's light. Just as there are different types of planets in our own solar system, exoplanets come in varieties too. While there are many subcategories that exoplanets can be further classified into, there are generally three main types: Jupiter-like, Neptune-like, and Earth-like. However, of the exoplanets we have discovered, hot Jupiters have been the most common to find, with other types being rarer to discover due to the difficult nature of finding them. Hot Jupiters are large gas giants having a size similar to Jupiter and extremely hot temperatures since they orbit really close to their host star. This is the type of exoplanet that is most easy to find because they produce the clearest transit as a result of their large size and close proximity to their star. Next slide. While transit methods are the most common way of finding exoplanets, this method does have its own limitations. For one, it is really hard to find smaller exoplanets that orbit larger host stars because the graphs their transits produce have dips that are too shallow to notice. Also, it is easy to detect false positives or graph transits that look like they were made by transiting exoplanets but were actually caused by something else, like brown dwarfs that look similar to exoplanets or stars orbiting each other in a binary star system. Next slide.
So in researching these exoplanets, there are two goals of our procedure. One of the objectives is to use the data to examine the changes in brightness of the stars, since the dips in the magnitude demonstrate an exoplanet in transit. We measure the brightness with its flux, which is the amount of energy from the star that reaches whatever is detecting it. The other aim is to determine the mid-transit times of the exoplanets, which is when the exoplanet is directly in front of the star. These times are calculated in Julian days, which are the amount of days since January 1st, 4173 BC. Next slide. In this project, the procedure started with collecting the data. The images for the data were taken over a period of a couple hours using the CCD cameras on SARA telescopes. SARA is an association of colleges and universities that operate 3 telescopes around the world, those being SARA KP, SARA CT, and SARA RN. East Tennessee University is part of that consortium, which is why we were able to access these images. Next, these images must be calibrated since there are external forces that affect the image. Calibrating the images uses 3 types of frames: flat frames, dark frames, and bias frames. About a dozen flat frames are taken and then averaged in order to account for the noise and dust in the image. These are taken by pointing the telescope at the sky at a uniform surface. Dark frames are used to eliminate hot pixels, which are when some of the pixels of the CCD camera generate an electron as if they were struck by photons when they really weren't, creating star-like particles in the image. Dark frames are taken with the camera shutter closed to detect the hot pixels so they can thus be subtracted. Bias frames are 0-second exposures to cut out the tiny electron current the CCD can detect from electrons that are just generated from the camera being on. Next slide.
AstroImage J is the primary program used by astronomers for general photometry. There were 2 different ways in which we looked at these transits using AstroImage J. The first is individually selecting the target and reference stars for each data file, and then once the reference star's magnitudes are inputted based on data from the star chart, the target star's magnitude is then calculated by the program. This process is repeated, and we plotted all of the results on an Excel graph. The second way we examined the transits was compiling all the images at once for AstroImage J to analyze. The same process of identifying target and reference stars are used, and the program can then identify the corresponding stars for all of the images. A graph of the target star's magnitude is then produced, where we can visualize the transit. However, even when doing all images at once, AstroImage J was an unideal software to use. Instead, we primarily used another software that has better user interface and is more advanced in order to create a best fit line, and that was Holloman Photometry Software, or HOPS. Next slide.
All right, I'll be walking you through the process of making a graph that shows this dip in the light curve with the HOP software, as Ethan mentioned. So the first step is to import all of your images into the HOP software, and these images are in the form of FITS files. This stands for Flexible Image Transport System. And so after clicking select change directory, you point it to the directory with all of your images. And then in this observation files, you type in the first letter of what the star is, and then it should show how many files or images you have of the sky. And in this case, we have 85 files. The next step is to click on the Show Header button, which essentially displays the metadata about the images. It shows who took the images, with what filter did you take the images, from where did you take the images. And after looking at this header data, you can fill in the filter, the camera filter. Then the next step is to select the target star. What star are you actually looking for? And so in this case, it was WASP 43. WASP stands for Wide Angle Search for Planets. And you should just type it in, it'll identify star if it's in the HOPS database. The last step is to identify the location of the telescope. And this specific, this imagery was taken from the CTIO telescope in the SARA consortium. And so these are the latitude and longitude coordinates for that. And so after that, you just say save options and proceed. and you move on to this step, which is identifying the target star in the image and then the reference stars. So this can be a tedious process because sometimes you have to identify the star you're looking for in an image like this. And so this is a hard process, but then there's this option which says plate solve image, which essentially identifies the star in the image for you. And the target star is this red, is what this red arrow is pointing to. And these blue dots are the reference stars. And their purpose is to essentially make sure that there's no abnormalities in the sky that's changing something in the brightness of all these planets. So they're just a reference. All right, now when you run the photometry, it should go through sequentially all 85 images in this case, and it should identify dips in the brightness that each star is emitting. And as you can see, with the target star, as it goes through these 85 images, it identifies that there is less brightness at some points, and this is the dip we're looking for. Whereas in the reference stars, it's sometimes noisy, like this comparison star, but it's supposed to be like this, where nothing's happening to the star. And so after you generate the graph, this is what it'll look like. On the x-axis, you have time, and essentially you're looking for this dip in the light curve. So on the y-curve, you have the relative flux, which is an astronomer's term for the energy which is emitted by a star, or the brightness. And so you can see on this graph, bottom left, that there is this dip in the light curve for the specific star. And the x-axis, as I said, it's time in Julian days. The amount of time which the exoplanet is transiting the host star for can give you an idea of how large this exoplanet is. It could give you data on the radial velocity of the planet. Another thing is that if this dip is larger, that means more light is being blocked by the exoplanet, meaning that it's either larger or the host star is smaller. So you can extrapolate data like this. Moving on to results.
So for our results, we were able to detect transits for multiple exoplanets. On the left is a graph for WASP-98b, which was discovered in 2014. Some general information about this exoplanet is it's a gas giant with a 3-day orbital period and a planet mass of 0.922 Jupiters. And according to the best fit model generated by HOPS, the predicted mid-transit time occurred on 2,460,282.59349 Julian days. And the observed mid-transit time occurred 3.3 minutes before what the model had predicted. Next slide. Another transit we detected was for Kepler 41b, which was discovered in 2011. It is also a gas giant, and it has an orbital period of 1.9 days and a planet mass of 0.56 Jupiters. According to the HOPS best fit model, the predicted mid-transit time occurred on 2,460,156.46348 Julian days, and the observed mid-transit time occurred 1.2 minutes after what the model had predicted. Next slide.
All right, so moving on to our third exoplanet, WASP-135b, as you can see by the graph, the dip is very shallow, even though this gas giant has a planet mass of 1.9 Jupiters, which is a little bit strange, but nonetheless, it is a gas giant. It was discovered in 2015, and its mid-transit time is 2,460,155.43458 Julian days. And it was observed 7.2 minutes later than expected. And it does orbit a relatively cool G-type star, which is very faint to be seen by the naked eye. Next slide, please. And looking at TRES 5b, the dip is much deeper, and it is also a gas giant as the other three were. It was discovered in 2011, and its planet mass is 1.79 Jupiters. And it does orbit a K-type star, which is also another relatively cool star, too faint to be seen by the naked eye. Its mid-transit time was 2,460,183.47864 Julian days, and it was observed a little bit before than expected. Next slide. So in looking at the overview of all of our exoplanets, we can see that we have a small sample size of only 7 exoplanets, so we can't really conclude much. However, there are some things to note from this data. For one, WASP 96b has the earliest mid-transit time, so we can see it dip in brightness first. And in looking at the exoplanet size, these exoplanets are similar to or greater than the size of Jupiter, as you can see the size of exoplanet column. And then lastly, WASP 135b is the biggest relative to its star, 16.8% of its star. However, it does have one of the shallowest dips, so that is a bit interesting to note. And another thing is that this star also has the biggest disparity between the time it was expected to transit and the time it actually transited. Next slide.
While most of the exoplanet transits we looked at have a confirmed exoplanet orbiting the star, that is not the case for TOI 2823b, or Test Object of Interest 2823b. While the photometry analysis we performed created a relatively significant dip in the star's brightness, the dip was sporadic and not exactly clear. Hence, the HOPS program could not produce a line of best fit for the transit, but these are promising results for a possible new discovery. We were still able to calculate a prospective mid-transit time due to the dip, but not much else could be concluded. Next slide.
Some of the highlights of our project was we were exposed to observational astronomy techniques that were practiced by scientists worldwide.
We were able to perform real-life data analysis using specialized software.
We were given the opportunity to contribute to and submit data to the NASA Exoplanet Archive.
We were able to engage with the CEAS e-learning curriculum, which guided us through the fields of Earth and space science. And we also got to learn about Python data visualization through these softwares that we used. Okay, some personal reflections of the CEAS program. I personally loved the opportunity to engage with astronomy data, image data at one of the largest space and Earth research centers in the world. So it was a great opportunity to meet my fellow peers, be mentored by our mentor. Yeah.
The CEAS program gave me the amazing opportunity to work with astronomical data sets and applications. I'm so grateful I could work with this team and with the Exoplanet Transits project because it guided me towards a career in engineering and astronomy.
The NASA CEAS internship program gave me the opportunity to work with other high schoolers in a scientific setting to pursue my passions as a student. CEAS was able to provide me with a project adequate for high school students where I could harness my background knowledge in astronomy and astrophotography and still be able to perform meaningful research with the team. This experience both propelled and replicated what I hope will be a future career in astronomy.
This internship was an amazing experience for me. I learned a lot through the e-curriculum and also through our mentor and my peers. And this project has taught me a lot and improved a lot of my skills from presentational to software to data visualization. So I learned a lot, and it allowed me to pursue my passion in astronomy by engaging me in really hands-on experience. And it also gave me the opportunity to benefit the scientific community by researching exoplanets, which is a common research topic and a very important research topic. And it also allowed me to use the Python software to graph and visualize data that we received from outside sources, which is a new experience. So I'm forever grateful for this opportunity in NASA season.
For me, CEAS really gave me the opportunity to learn from an experienced astronomer. And like as a high schooler really passionate about physics, it's really a once in a lifetime opportunity. So I'm really grateful to CEAS and Dr. Rutherford for the opportunity.
And while the process of working with real data seemed intimidating to me at first, the work I did with my mentor and my peers really made it seem less daunting, and it let me head start my career in space science.
Yeah, this CEAS experience has taught me so much thanks to my wonderful mentor and peers. I had no idea about exoplanets or transits before this program, but this program really unlocked a new fascination and it intensified my passion for astronomy.
These are some of the people and organizations we'd like to acknowledge. Firstly, our mentor, Thomas Rutherford. He really guided us through this entire process. And obviously NASA Seas for allowing us to work on this project, and University of Texas at Austin for giving us the resources to embark on this project. East Tennessee State University is the university that our mentor works for, and they also provided the Zoom meetings and also the data for us to work with, which is also thanks to the SARA Consortium, which is a group of telescopes that we got data from. And AstroImageJ and HOP software, as previously mentioned, it really helped us analyze the data and really facilitated the whole process. And of course, our parents.
These are our references. Thank you very much for taking the time to listen to our presentation.